Hello and welcome to a beautiful day on our Lord Odin's day. So hopefully everything should be live and everyone should be able to see everything that's going on. So I am going to share the link to all of the appropriate places so that people can see what's going on. Let's find out here. Oops. Put them into there. And put them in the other appropriate places, such as that place. So, welcome to the wise day that is Odin's day, Woden's day, Wednesday. And today we're going to be doing something slightly different. So previous two streams I was working on my WASM assembler, which I have pretty much completed now, and I was working on actually the language that I was going to lower to the WASM. I was pretty much just making a minor knockoff between somewhere between C, Pascal and Go, and just go there. I don't need all the features of all those languages, obviously, and I'm just trying to keep it very simple, but we're not doing that today. Today, if you can hear me all clearly, is I'll be working on, well, not working on, but actually showing people actually how the Odin compiler works. Because I've had many requests regarding a lot of this, because many people have actually wondered, okay, how does the compiler work for Odin? So if you've got any questions during the stream, please be free to ask as many as you'd like, and that's fine. Sorry, it's YouTube again. I literally couldn't get Twitch to work. That was the only reason I would have been using Twitch straight away. Twitch was not doing anything, and I have no idea why. But YouTube worked perfectly fine, so it looks like I'm using YouTube today. That's it. Couldn't get Twitch to work, and I have no idea why. So, let's explain the Odin compiler. So, I might actually just get my tablet penny thingamabob, drawing tablet. Whatever that's called. You know what the words are. I don't, but you should probably know what the words mean by that. Okay, so there we go. Graphics tablet, drawing tablet, something, what are they called? Whatever, that thingy. So I've got Milton in front of me here. This is a very old version of Milton, actually, which I should probably update it. But let's change, set background color. Let's go for change the hue and saturation. Yeah, that's good enough. So generally, for a compiler, you have many different stages to it. So the first stage many people have is, is the Tokenizer. Oops, thank you. Or some people call this Alexa, or some people call this the scanner. They're all the same word, they all mean the same thing. What this means is it takes your program, in your text, and turns it into tokens. It does a lexical analysis, it scans the thing, it tokenizes it and turns it into tokens. I prefer the word tokenize because it does what it says on the tin. Because that's what it does. Yeah? So that's the first stage. So once you've now got the tokens, you need to turn this into something you can deal with. So the next stage is you need to parse this. So this is the parser. I apologize for my handwriting. It's very difficult to write on a tablet and do it here. So we have the parser stage. So this turns this into a thing. So these are the tokens. Turns this into a tree-like structure, an abstract syntax tree. So the AST. That's what that does. So your code is now expressed in this abstract syntax tree, which is made up of tokens. Simple enough. The next bit in the compiler is simply enough the checker. So this gives all of the semantic checking to the tree. So the tree itself is pretty useless without any type checking or semantic checking or constant checking or anything like that. So you need to do this. So this is the complicated part of the compiler, really. So this, and that's fine. So this, many people would class, so I go to a red here, most people, yeah, that's better, would class this as the front end. Yeah? So you tokenize, you parse, and you check. So most people class this as the front end of a language. The next stage in the Odin compiler is what I call the IR, or is the IR backend. So this is the middle end, what I class this as. So this is the middle. And this is LLVM, effectively. And there's two backends at the moment because I'm trying to transition from the old approach that I did to the new approach. And eventually the old approach will be completely removed and the new approach will be the best way of doing things. Well, not the best, but the best way of doing things with LLVM. Yeah? Can anyone hear me? No? No sound? Otherwise, I'm just going to... Okay, so I'm just checking. Sorry, I was just checking. Someone said there's probably no sound. I'm just checking through. That's good. So that's the middle end. So the middle end converts this AST into an intermediate representation. That's what IR means. So for people who don't know, this is intermediate... Oops. Representation, which can then be dealt with a much more easier approach. Okay, so that's the middle end. And then what we have after that is the back end. So this is the back end. So the back end in this case is many different things. So we have LLVM, which does the optimization. So this actually does multiple steps. It has optimization, lowering to machine code. We also have the linker as well and anything else related. So effectively, this is all a compiler is. Compilers are pretty, in a sense, linear in their operations, and you kind of have to do them from there in that regard. So you got your tokenizer, your parser, your checker, your intermediate representation, the backends, the optimization, lowering to machine code, and then the linker. Currently, we effectively have control, and I'm just going to do a nice color, let's say green. Odin has this control, kind of, and I'll just do a fuzzy yellow color for the middle end. Yeah? So these are all kind of separated up. So Odin is completely, I've got all control of the front end. The middle end, I've kind of got to match it to be LLVM, but I can control how it's generated and such, especially with the new LLVM backend I've been using. The complete backend, I have no control over whatsoever, really, and I'm at a whim there. So if I ever wanted a fast backend, because LLVM is pretty slow actually, I would actually have to write my own backend, which would take the IR, lower it to machine code, and then pass it to the linker. But that's effectively how I think about compilers. Many people may not say there's a middle end and say this is part of the back end or say it's part of the front end, but to me, that's the middle end. It makes sense because you're joining the back end and the front end together. Okay, that's clear. So to make sure we understand what the compiler works, especially for Odin, is we're going to understand the tokenizer first and all of the intricacies that are in the Odin tokenizer. So we're going to go to this file. So this is probably a little bit too big. But yeah, at the beginning of this file, which if you want to follow along at home, is download the source code of Odin from the Odin GitHub page, which is easily accessible here at github.com/odin-lang/Odin. And you'll get the Odin source code. Download it here, download a zip for the latest one, and try it now. We have some CI failing. I never really noticed that, but that's not a problem. I'll fix that later. It seems to be it's probably failing for one of the other operating systems. So we're going to go through here. So it's the tokenizer and different things. So at the beginning, we have a massive X macro. And this is effectively so that I can have better generation of tokens. So this is a big list of different types of tokens we have in the language. So we have a token kind, and then the name of the token, which is this enum I actually use, and then the string variation of it. So effectively we have an invalid, EOF, and comment tokens. So invalid means this token is completely invalid, makes no sense. Sure. Someone's saying actually, let's first put the Odin website in the description. Yes, that is a very, very good point. That is actually a very old description in there. I'm just going to put let's put the Odin website in there as well. Oops, daisy. We're not. This is very out of order. That should be absolutely hunky-dory. Yep, let's save that and add that to the new description. Thank you. Yeah. Thank you. Thank you, this drunk Dane. I know what's the problem now. So good. Thank you. So when we have all the different tokens, so Odin has comments. We even actually, so many different languages don't necessarily do this, but Odin actually passes comments as a token. And the reason for this is actually for a future feature where it's going to be automatic documentation. So you can actually associate comments with a declaration, so it'll have easily automatically generate. That's the reason why I pass comments, because many tokenizers just completely skip over them and just ignore them, and they're not treated as a token. But for Odin, we treat them as that, because then we can group them and put them into like a comment group. We also have different types of, I call these basic literals. We have identifiers. We have integers, floats, imaginaries, runes, and strings. They're just different types of tokens. So Odin is not a self-hosted compiler, and the main reason behind that is because I think self-hosting is usually just a bit of masturbatory fun. It has very little gains in productivity. I can understand why it'd be good, and Odin will be eventually self-hosted for the most part, at least the front end. Not necessarily the back end, but the front end will be. And just because it's not worth your time. Now, not to be very, very clear, I do want to have quite a simple self-hosting version soon-ish, so I can get some nice metaprogramming tools out to everybody else rather than just myself. So you can actually pretty much, the whole point of metaprogramming I want in Odin is that you just have the Odin compiler as a library, you import it, and you pretty much modify the compiler however you damn wish. So I cannot please everybody with metaprogramming, so I just need to give everyone the tools to do what the hell they want. Short answer of it. That's it. So going through this, again, you can see there's different lists of different type of tokens and different operators here, and then there's a big list of keywords. So Odin does have a minimum set of keywords, but it's still quite a lot actually, and I wish I didn't use as many, but some of them are kind of compromises like that. Good evening, everybody. Welcome to the stream. More people coming on. That's wonderful. So we're going to talk about this. So we've got all the different token kinds, and I use this X macro little trick. So I can set the enums here for the types, and then I can set the token strings here. So in Odin, I have, in the Odin compiler, I have a string type, which I define here. And the string type is just a U8 text and a length, pretty much, and nothing else. And it's very simple, and that's all that needs to be done. So we've got lists of that, so it's nice just stringing. So we have many different things in here as well. So the idea I have here is a token position. So this defines a token position in wherever it is. So it defines the file, which is just a general string, the offset in that file itself, the line number, and the column number. Now the column number is in characters, not in like spaces or tabs or anything, just characters. And the reason for this is that you cannot know, full stop, cannot know unless the text editor told it, you explicitly told it, how big a tab is in times accounts. Because some text editors treat if you text Sublime Text, this says column 5, even though I use tabs, because it knows I use 4 tabs, sometimes I use 8, and now it's got to the 9th column, it says there. So it's very difficult to know. That's all it's the case. This one's just a nice little comparison operation that you do in C style thing here, and then I just got the operator overloads for C++ just to make it a little bit easier. So a token is now simple enough. You combine the token kind, the string, and then the token position. And that's a nice little thing there. We've got some helper functions here. Another thing here I have here is a global error collector. So this is an error collector which just takes into account any of the errors I have in strings or the any of the other information here. So for instance, if you're making a error, let's go to the actual error call, a simple one. For instance, syntax error here, it'll add it, goes through, so we've got normal error, we take a token, it'll go into the list and find, okay, it needs to call this thing here, and it'll do all the stuff. So it'll lock it, increase the error collection count. Now I use a mutex here for the main reason I do want to stop the world. I don't actually care about how fast it is if there is an error and I'm trying to report an error. It's not a big issue in my opinion. We go through all this big list, we print out, and then we stop. And if we hit too many errors, like maximum errors, we completely just quit from the entire application. That's the general approach I have in here. Rather than just have like infinite, like 1,000 different errors. If we've just hit like, let's say 20 errors, I can't even remember what the actual number I actually set to be the maximum. 36 I chose, just a random number, of course. 36, brilliant number. The best, in fact, the best. That would be it, to be honest with you. So there's nothing kind of special going on there. So that's just the error handling. So there's a lot of crap in this file because it does actually a little bit too much, to be honest with you. So now we're going on to that tokenization stuff. So we have different tokenizer, the tokenizer state, and then the tokenizer itself. So the tokenizer state is so that you can store state for the current tokenizer and restore it, because there are times when you're tokenizing things and you want to try a little bit and see if it tokenizes in a certain way, and else you just fail. It just revert back if it wasn't the good case. So this is more of a look ahead testing approach and then revert back to the initial place. It's just a tokenizer state, this is what that mimics, the same thing. If I was using Odin, I would literally just say using on all this, but I don't need to. I like save and restore the tokenizer state, absolutely fine. This is a tokenizer error thing, just makes it sure it's part of the tokenizer, and fine. So now we get into the absolute magic, and the absolute magic is this, advance to next rune. So Odin is a fully UTF-8 compliant language in the fact that all source codes are assumed to be UTF-8 and they will be parsed correctly in that sense. So we go through our little tokenizer here, and we have a read cursor and the read current thing and the end pointer, and we go through the runes here. So what we do is we set the read cursor to be the current one, and if there is a new line, what we then do is say, okay, the beginning of that line is where that cursor is, and we increase the line count. Simple enough, very simple. And then what we do is we just read the current byte as the current rune. So we just treat it as ASCII. This is how UTF-8 works. If it's 0, then we've got an invalid null character somewhere in our data stream, the file, and then we just raise an error. But we can't carry on if it's just pretending the width was 1. Now, if we know this is non-ASCII, like the first rune in there is got the highest, most significant bit set, which again is more than 128, greater than 128, we now need to decode the data stream as if it was UTF-8. So we take in the rune and the width of that string. We then go through the rune and get the width, and if it was an invalid rune but the width was 1, we say this was an illegal encoding. The next one we need to check is to see if it's a byte ordered mark, because UTF-8 allows byte order marks, but they're only allowed to be at the start. So if it's not at the start, then it's completely illegal. Okay? If we are right past the end and we're not going to start, all we need to do is pretend we just output an EOF always. So we're at the end of the file, no more. This is just a patch up because there can be some weird tricks going on, and it's mainly just to do with error correction and stuff. So this is the iterator. So in many compilers or many tokenizers, all they would do is when you advance to the next character, you just increment this by 1, like point arithmetic. But no, Odin has to completely do UTF-8, and that's the way that I do it. Okay, so that's the first bit. Lovely, Jubby. Any questions? People going on? Probably going a bit too slowly, but trying to make sure it goes clearly. Okay. Good. So next thing is the tokenizer itself. Okay, just make sure I've got everything on Ghidorah, so I'm just replying to people. So now we've got the tokenizer stage. So the tokenizer this is initializing it, and what we do here is we pass in the full path of the file that we want to tokenize, and I have a little function that calls, it's pretty much file read entire contents. It's just file read and all it does is dump it to a structure, which is quite most of the time what I want. I don't want a mem map because that's actually not faster than you think. You usually just want to dump it into complete memory and just deal with it there. So you can modify it, you can read it, do whatever the hell you want. I check to see if it's valid, and if it is the valid here, then we put the data into here, set up the tokenizer, and start the first room. So we get it into the right place, we read straight away. If we notice the first rune, it's actually a byte order mark, we just skip over it and ignore it and go to the next rune in the actual character. And then what I do here is also initialize the allocated strings. So the allocated strings here are, because the tokenizer is actually completely multi-threaded, as in each file has a thread associated with it, we want to make sure that we can actually just pass and evaluate the strings in the actual compiler itself straight away. Yeah? Okay. Now, if there was a failure here, we just need to log it and tell what's wrong with the actual tokenizer, and so on forth. So destroy the tokenizer and here. So in Odin, whitespace, when we skip whitespace and stuff like, for instance, dummy stuff, we only actually have 4 different types of whitespace. Everything else is not whitespace. So we have a normal space, we have a tab, we have a new line, and we have a /r, the return carriage, the carriage character. Now that's all I treat as whitespace, and that's personally my preferred approach to doing things, because you don't need to get the vertical ones or the form feeds or any of that crap. You just have this stuff here, and this makes things a lot easier. So in Odin, the way that I handle things, welcome to the stream, Andrew, how are you doing? The way that I handle things here is that only treat \n as new lines, and these are just treated as normal white space. Now the way that I do that is because, to be honest with you, I don't really care about old-fashioned macOS operating systems anymore, where they treat return carriage as a new line. Virtually every other operating system will support the \n as a new line, or some combination with the return carriage and the \n. So if you just treat this as normal white space, then it solves most of your problems. Next thing here is just treating 4-digit characters, that's fine. And here, so actually let's get to the scan token number. This is actually a little magic, to be honest with you. So what's going on here? So we take the tokenizer state here of the seeing the decimal point, and this is pure magic. So if we've seen a decimal point before, then we need to offset the state and actually say it's going to be a float already. And then we go straight to scan mantissa. So a mantissa is just a digit value or an underscore, and we just keep that until it's actually found anything. So underscores are there so you can imagine them as digit separators. Very nice things. And then once we've scanned the mantissa, we go to the exponent stage, and we go with that first. Otherwise, we can do whatever we want. So if we start with a 0, we will need to check to see if it's specifying a specific radix space. So if it's 0 lowercase b, it's binary. If it's O, it's an octal. If it's D, it's decimal. If it's Z, it's dozenal. If it's X, it's hexadecimal. And if it's H, it's hexadecimal floats. So this is actually a little bit weird, but hexadecimal floats are not the same as if they were in C's hexadecimal floats. I absolutely hate them, and I understand them, but I just find them confusing, because usually I just want the binary representation of a float, and that's exactly how I want to represent it. I don't want to explain the, oh, here's the sign, here's the mantissa, here's the exponent, and they're all in hexadecimal. I'm like, no, here is what I want. And just give me here's the bit thing. And again, I only just treat it as base 16 and make sure it's of length 8 or 16. And if it's not, error then. If we see a 0 but it's none of those things, we're just going to treat it as if it was a normal string and do the same thing. So we have all these go-tos everywhere, and you can do cool stuff. Yeah, so the AST part is going to happen very soon, by the way. The actual tokenizer is about done, by the way, Andrew. So don't be worried. So there's all these different things here with the different fractional stuff. So fractional stuff is anything with the decimal point, do that, great. And what I do here is I peek to see if there is another dot, because it could be an ellipse. And if it is an ellipse, just go straight to the end and don't even go any further. If it is an ellipse, that's great, we can keep going through. In exponents, we check to see if there's an E, and then we got the different things on here. And the last thing we do is we check to see if there's an IJ, and then because that's an imaginary. Very simple. Now we got the escape stuff. This is all for strings, so like the backslashes, and see if they're all valid and see what things they do, and they parse them correctly. So that's pretty simple. And here's now the meat and potatoes of the entire tokenizer. The tokenizer here is the get token, and it's pretty much simple. We just keep asking to get tokens. So here is we first need to check is if the first letter of this new current rune is a letter, we then treat it as if it's going to be an identifier. But here's the thing about this rune letter, it's completely UTF-8. So Odin fully supports Unicode characters, and I had to use the UTF-8 proc library to get the categories, and I'm not a big fan of it because it's actually a crap library. It's absolutely awfully written, and there's bugs in it all the time, and it's like, oh. But it does the job for me at the moment, and until I write a new one. And what this does here is I can get the letter categories, and I've defined these to be the letter categories that I want to define as a letter. It does short circuit it, so in the fast case it will do this. So if it's transitive letter, it's going to be an underscore, or it's going to just be an alpha, just do that. In the other case, so this is the slow or the cold case, then it will do the UTF-8 case here. Absolutely wonderful. So then for the Unicode, we just check to see if it's a Unicode letter or a Unicode digit, and we keep incrementing the room, and then we create it. Now, one thing I've known is a little trick here is that all keywords are greater than 1. So if the string is greater than 1, then we know it could be a keyword, so we need to check through it. This line here is I'm just checking for deprecation. So not in was originally not in, and then until I put an underscore in, that was correct. The other one here is to check for a number. Again, this is just setting the tokens. It's very, very simple, and it's the 0 and 9. That's fine. So that's just checking a number. And now after these big ifs, just short-circuiting ifs, we go to the big thing, which is a massive switch table. So we check to see if it's an EOF, we say the token is an EOF, done. If we see a single character chart, the quote mark, then we know it's a rune literal. So we said it's a rune literal, and then we parse it correctly, because you're going to have /u and define the number of the interval. So you have to make sure we got the scan escaping correctly. So scan the escapes and do that. If it's valid, but it's not equal to 1, then it's been parsed as if it was a string. So it's an invalid rune literal, and it was actually just a string instead. So but we carry on. We don't want to fail too much. We want to keep parsing. We don't want to stop. You need to try and do as much as possible. We then unquote this, and we turn this, unquote the string, again it's in parallel, so we do all these cool stuff. And quoting it could be like you've got a /u, 0, 0, whatever, defining it correct. We check to see if it's success, and if it is success to us, it means it's been allocated, but not, we need to add it to the allocated strings. Very simple, so we can free it later. So that's all that case, and if it's failed, we'll just tell it's an invalid rune literal, done. The next cases are for the strings. We have the backtick, which is the raw literal, and the speech mark, which is for a normal string, which is you haven't allowed for escaping. And we just handled those code, and then the logic is the same here. Very simple. We have now got a dot. So this is a period. And if we look for another period, then we know it's ellipse. And if it's a period, and then a less than sign, we know then it's a half a range. If it's a dot followed by a number, then we know it's a decimal. And if it's nothing else, it's just a period. So these are pretty much the simple thing. You see what goes on throughout this. And it's pretty simple what goes on. And that's pretty much the entire tokenizer. Hopefully that is clear to people. So let's go on. So now let's go on to the actual parser and explain all of this insaneness. So there's a lot of actually stuff at the top here. And it originally wasn't in here, but I actually had to add it for performance reasons, so I'll explain later. But let's just skip all this nonsense and let's go to the meat and potatoes of the entire thing, which is ignoring the parser data and all that. Let's go to the AST. So in Odin, we designed the AST to be actually a discriminated union. So if I get the parser open again, we can actually see this. So this is the base AST struct, which has everything in it. It has an enum to define the kind, which is the enum. We have some state flags and some viral state flags. So the state flags are kind of stating, define things at the like the expression level, or the statement level, declaration level, like, oh, no bounds checking on this, please, and everything else is gone there. Viral means it affects upwards. So there are only one or two viral states, if I can remember correctly. There's one viral state, and that's to check if it contains a deferred procedure. And that's just for checking something in particular, like there's something else going wrong there. That's just for the compiler's sake. It's not technically needed for the language, but it really helps with error checking. That's the reason why it exists. There's a boolean to check if it's handled. There is the file pointer for that AST node, so it's associated with it. There could be an associated scope with this node, so we just put it on there as well. And then there's a type and value. This contains the type, value, and addressing mode for the node. So, oops, took a picture. Didn't mean to do that. Oh well. Let's close that. So type and value contains the addressing mode, the type, and the exact value. So an addressing mode is a little bit confusing to some people if you're not used to it, but let's explain it anyway. So in addressing mode, this is kind of like R values and L values in other languages. But Odin has a little bit more than just an L value and an R value. We have, ignore that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 different addressing modes. So compared to C, which probably has about 3, and C++ probably has like 5 or 6, Odin has 11. Now, this may seem like a lot, saying, hey, I thought Odin was meant to be a very minimalistic language. Why the heck have you got so much? And the short answer of it is just because it kind of needs it to feel right. So we're going to explain it. So the first one is the invalid addressing mode. So this is when something's gone wrong, or it's just not actually addressing mode whatsoever. It doesn't need to be done that, so that's there. The next one is for the no value. This is void in C. So Odin doesn't have the concept of void in its type system whatsoever. And this is by design, to be honest with you, because personally, I didn't want the concept of a void type because it mucks up a lot of issues in the type system. Now, I understand where the benefits come from, which is when you're doing parametric polymorphism, generics, as many people call it, templates, or whatever. It's not technically templates, but yeah, you know what I mean. Stuff like that. They will want to have generic things. You allow void. If it turns a void, you want to allow it. Now, in my opinion, I think that's not a good idea in any actual practical case. But that's fine. So Odin has no value. The next one is a value. So this is a computed value, mainly at the runtime usually. And this is an R value, so in C in that case. There's the context variable. Now, context has to be a different addressing mode because it has very special semantics. For instance, if you assign to a context variable, it'll probably generate a new one on the stack, so then you can pass it again and it'll change it for that scope. So you need to have different semantics of how things will be handled. There's variable addressing mode, which is an L value. So it means this value is addressable, as in you can address it now as if it was a variable. Another one is a constant. So this means that this is completely known at compile time, and that's setting it's there. So you can't address it, but it is compile time known. It's different to a value, which is known at runtime. Constant's now known at compile time always. There's addressing mode of type, as in this is a type. This expression is a type. It's not a value, but it's a type. There's a built-in. So this means it refers to a built-in procedure. This is actually a little helper. We didn't technically need it in theory, but it actually helps a lot just adding it to the addressing mode. Same with the proc group. This means this is a procedure group. So this is a group of overloaded procedures, and then you can select from the procedure group as you go along. So they have very different semantics. There's map index, which is slightly weird. So on the left-hand side, it acts as if it was a variable. So map index contains the maps. So the map is a hash map, contains the value and an index. So on the left-hand side, when it's being assigned to, it is being acted as if it is a variable. On the right-hand side, it acts as if it's an optional OK. So it actually means it's on the left-hand side, it's a set. On the right-hand side, it's a get. Now, some people may know I actually do kind of regret adding a map type into Odin, mainly for the reason that there's a lot of complications with it. And I think a dynamic type was a good idea to add, but the map type was probably like, yeah, it's great for doing like prototypes, just getting something quick and up dirty. But really, is it the best idea when sometimes you want a better hash table or one that's more in check things, because the Odin map type doesn't allow you to change the hashing procedures or the memory or anything else like that. But Odin now, I'm adding new data structures to the table. The next addressing mode is the optional OK. So it acts as if it's a value on the right hand side, but if the left hand side has two parameters, so there's going to be space for an optional boolean. And the last one is to check if this is a structure of array index variable, which is a little bit complicated, but it's to work with the SOA data types in Odin, and it makes it feel correctly. So they have different semantics. So that's addressing modes. Now, I know it may sound I've spent a long time on this, but the main reason for this is because Odin's addressing modes are quite important for its type system, and it's quite important to make sure, that's how you've got it to feel correct. Again, please ask any questions if you've got any going on. Thank you. Okay, so that's what's in the type and value. So if we go back to our AST here, we can see all the different types of ASTs. And as you can tell from here, I stored it as if it was a big discriminated union. And I did it for this main reason. The main reason I did it this way is because that means that every single AST node is the same size. And that means you can actually have a very nice allocation strategy going on. And also because you can just completely memcopy it. So if you need to duplicate a node, which is very useful for when you're doing like parametric polymorphism, or if you're doing something like macros or something like that, you can just allocate the entire node and all its children. And all you do is you allocate a new node, you memcopy it into place, you patch up all the pointers and just recursively and do that. It's a much simpler approach, it's faster. However, this approach does have a disadvantage in that it does use twice as much memory. So I profiled it and it uses twice as much memory as if I did a subtyping approach, which is very compact, more like a general inheritance. But this approach, I do kind of prefer it usually in C. So if I was doing this in Odin, I actually prefer the subtyping approach because I actually have complete runtime type information. I can do whatever the hell I need. And it's just a little bit easier in that regard. So there's all that. Oops. Just need to get myself a drink. Tonight's drink is bourbon. But yeah, I thought I was going to be talking a lot, so I need something to soothe the throat. That was all about it. Not milk. Oh god, milk's the worst thing you could probably do, yeah. But yeah. There's probably a list of things. If you do ever do radio presenting, they'll tell you what things you can and cannot drink if you're doing speaking. Water is the top number one you should be doing. Tea is fine. Coffee's usually okay. Alcohol can be fine. It depends on the person usually. Milk is a bad idea because it coats the throat and it makes it horrible. But yeah, okay, I'm getting distracted. But hey, that's the streams you come to join, because that's me. I get distracted very easily. But yeah, so these are different AST types. You can see I've just put the macros and they're just massive. It's just a big X macro. Because what this AST kind thing, it defines this thing, which is the name of the struct, and also the enum at the same time, and it does it that nice little fashionable way. So these are all the different things here that's going on. And we have some nice little things here, like, is this an expression statement? It's a complex statement. Now, complex statements mean a little bit more complicated from the name. And declarations type, and it's a when statement. I can't remember why I needed this, but there probably was a reason for it. And then I have the AST allocator, which is I have a global allocator here, which is an arena, and it is completely thread safe, and it just allocates. Oh, they're all the same size. Go done. So now we go into the parser. Now we're going to the parser.cpp, and what I'm going to do is go right to the bottom, and the bottom is where we are doing all the magic work, which is parsing the packages. So when you're looking through the compiler, it goes straight to the parse packages stage. You pass in the parser, which is the magic thing that does all the parsing, and then your initial file name. We are setting up the threads because we are setting up a nice little work queue to do all of the parsing, as you do. And we do it that way. We initialize the thread, and then we initialize the thread pool up and be done. But we don't start it because we don't add any new work to it yet. So the first thing we need to do is get the initial file name that was been passed in. So this file name could be either a directory or it could be a normal file. Now, if it isn't a directory, we need to make sure it ends in a .odin for the time being. And if it doesn't, we say, look, we expect either directory or a .odin file. So I'm enforcing a file extension, an Odin at the moment. And that's because of how the package system works. I look for the .odin files to get every single file in the package. So I needed it to be enforced. Go here, we can ignore the generate docs for the time being. But yeah, so the first thing is, before I do any parsing, other than the initial file, I make sure I parse the runtime. So I need to make sure that you get the full path of the runtime library and then try do an import path and parse all that, and everything else it depends on. The reason I need that is because the runtime has some nice little things, dependency, and it's kind of just to keep it simple. I don't have to define everything in the compiler. Some of it's kind of defined as like bootstrapping code. The next thing I have to do that is then I start the initial path. So I define each package to be a little thing. It's just helpers in the compiler. This is the runtime package, and then this is the initial package, and then everything else is normal. So then I start the thread, and then I wait for the processes to be done. And when it is done, we get the errors because they'll all get compiled up, and then we just print them out because we don't want any things go wrong. So if there have been any errors in the thread queue, we just want to quit from this entire thing and be done. We don't even want to go to the checker stage. We just want to say, right, there's been errors in the parser. Great. Just stop. That's all we need to do. So hopefully it's making clear again. Please ask questions. So when you may be asking, look, I only have this file, but the try import adds more to a work queue, and the queues just add more work to be done. Oh, there's more files to be done. Great. So when I try and add import, it adds to the file. It checks. First, it checks to see I'm doing a lock here. Now I probably shouldn't do a lock, but it's not a bottleneck at the moment. But yeah, fine. So I first do a file mutex lock and do a defer on the lock. And I check to first see if I've actually imported this file before. And if I have imported this file before, I just exit out of the triad path because it's already going to be handled later. So it's fine. So the entire Odin compiler is kind of out of order on a per file basis. I've been discussing with someone recently saying, oh, they wanted to try and design a language where they could actually multi-thread on the file itself. So you can actually find very discrete marks in the file and multi-thread them that way. And I'm not a big fan of that approach because if it's a textual based thing, usually that's quite linear in its nature, and you can't really find those distinctnesses to where to find the things because they go a bit crazy is a short answer. So I'd rather just do it on the file basis, which is quite a natural unit to deal with. That's fine. So that's all of that. So once we go do and try the stuff, we then do all of the thread work. Now we've started this thread parser pool here and parse the thread pool. Whoops. And it's a global variable, I think, and then we just add more tasks to this. So we have a parse worker proc here, and we can do process the imported file. So we can go to that procedure now and be done. And oops, now we need to go to here. So this is very simple. So the Odin parser is a recursive descent parser because they are the best and they are virtually the only ones you'll ever need to write. I'm not even joking about that. You may learn them in school. I have no idea because I never did programming at school. But yeah, recursive descent parsers are pretty much the bee's knees and the only way you need to parse. They are the simplest to write, they're the simplest to maintain, and they are pretty damn fast. You could probably make something else that's probably a little bit more faster in a more esoteric way, but it means sometimes it may be a little bit harder to write and maintain. So unless the language is quite small, I wouldn't recommend it. But recursive descent, because in a sense your trees are very recursive data structures, so they can all attach to each other. So you want to do it that sort of way, in my opinion. So that's kind of how it works. Now we can explain some of like the recursive structures. So we can go to some of the crap here and actually just go to some basic example. Like for instance, actually let's go to parse expression. So in parsing expression, we actually parse a binary expression. Oops. And the binary expression thing, this is actually pure magic. This allows for arbitrary token precedence. This is something I kind of came up with, and I actually loved it when I came up with it. So what this does here is allows you to parse a binary expression, and it takes into account the precedence as you're doing it. So you have the precedence in, and then you're going through the precedence in this main loop, and then you have an infinite for loop inside, and you're trying to sort it. So if one people to figure this out, it's a nice little algorithm, it's cool. But this entire function is a bit of a hack. Unfortunately, Odin, its grammar has gotten a little bit complicated over the years, just because of what people wanted from it. So an example of that is with the new ternary expressions in Odin, where you have like x if condition else y, or the when as well, which is the constant version. They are treated as if they're binary expressions, but they are technically ternary expressions, so you have to treat them as an edge case. Otherwise, all of this code is very, very trivial, and you just treat it as another binary code, another binary expression, and then parse them to join them up. Like so. But the first thing when you get a binary expression is the first component of binary expression will be an unary expression, so single valued, which could be a thing anyway. So we have the unary expression, and in here we have different things. So the unary expressions, the basic ones, have prefixes to them. So there could be a casting operation, an auto cast, something with like an add, a sub, something like this. So add, a sub, like a not, a zor, or an and. We've got a period, which is for the implicit selector expressions, the lovely enum things. Otherwise, we go to an atom expression. So this is just a basic normal things elsewhere. So an atom expression is for what's the best way of explaining an atom expression? An atom expression is where you have an expression and then it has something on its suffix. So for instance, it could be an open parentheses after its suffix, so it's call. It could be a period, which means selector. It could be an arrow, which means you've tried to write C, and I just handled that case because I'm saying, look, did you mean a dot? Because we're not C. It could be an open bracket, which means then you don't do an index or a slice. Or it could be a pointer, which means it's a dereferent. Or it could be an open brace, and then it means it's a compound literal in that regard. And it just does a loop, and it keeps it going until it's done all the parsing. You can do a parse operand, and an operand in this case is the single units in your expressions. So you have like the identifiers, the undefined, the context, basic literals, which is the numbers. We have very built-in procedures. Now, these didn't used to be keywords, like they never needed to be, but I had to make them keywords for weird reasons regarding the parametric polymorphism. It's actually a bloody edge case, and it has to be that, but I really hated it, but it needs to be that for some reason. Well, it's because of also type of. Type of needs to be a specific type, and when you pass things, just put it this way, it's weird. We've got another one, which is a basic literal, which is the string. Theoretically, I could just go like that, and actually probably should have done, but it's old code. It works. Open brace in this case is just, it's going to be an unnamed type literal. Now, one thing I do here is you might see the left-hand side stuff. This is to check to see if your expression is on the left-hand side or the right-hand side of an expression. And the reason for this is actually, it's for two reasons. One, you don't want to have a compound literal on the left-hand side of an assignment. It makes no literal sense. So you just don't allow it. And also, the expressions within control flow, like ifs, fors, and switches, we don't have parentheses around our expressions. So we need to check to see, because a compound literal is the same, looks the same. So you need to actually say, look, okay, we're pretending we're in the left-hand side for the expression. And if we surround it by parentheses, then it's fine. But it is a nice little hack, and it actually feels correct. But that's why you have to track this expression level. And if you're on the left-hand side. So they both do the same thing, but they'll both counteract each other. But it's a nice little playing of stuff. But yeah, you can see all this nice little thing. There's loads of big lists of all the different hashes we've got in here. These directives. The inline, no inline. Procedures. It'll check to see if it's a group or a type or actual body. And so forth. Different other things here and so on forth. So this is pretty much the basic compiler. I'd recommend people reading it through because this is the general meat and potatoes of the compiler. So if we actually look at a file, we can actually explain what more we're going on. So if we go to the main.odin file, demo.odin file might be easier. That's some. So first off, I want to just revert things. I was doing actually a minor test earlier. It's just a Odin. I should have done this earlier. Revert. Yes, just revert that, please. Thank you. So now if we go back to the demo.odin file, we've got everything in here. So the design of Odin is a little bit, I've tried to keep it simple. Now the parser actually handles everything it can. It doesn't try to be simple or fast. It tries to be as fast as possible, but it doesn't try to be stupidly fast where it can't catch many of your errors. It's a nice little, you have to take this compromise between speed and, what's the thing? It's a compromise between speed and error checking. So effectively at the file scope, we have different declarations. We have the package declaration at the top, which is required for consistent ABI. We have import declarations, which are allowed anywhere, by the way. It's just I traditionally put them at the top. We have value declarations here. And we also have foreign declarations as well, and stuff like that. The only weird thing at the file scope that we allow are when statements. And notice they are statements, and they are not declarations. And they are the only statement we allow at the file scope, effectively. There are one or two exceptions to that rule as well, like directives. But in general, that's the other main exception to the rule, not like weird edge cases, like for doing extra things. But they're kind of different things. So we have foreign, all of them are just declarations at the file scope. So then within a procedure scope here, we allow statements and expressions and all that jazz, like so. And so on and so forth. So explaining what we just did here, going over a little bit here because I've been talking for about about an hour now, nearly 50 minutes. These are tokens. We then pass these tokens into a tree that we can deal with to put into a check-in stage. Odin does a little bit all full-on UTF-8 compliant and does a load of cool things. So has anybody got any good questions at the moment, or shall I carry on? Please, please, if I'm going too quickly or too slowly, please just say. It's very difficult to know because I'm so used to this and I've been programming in this for a hell of a long time. But I've tried to make it so it's very simple, so people can understand it. Like the tokenizer and parser is mostly quite simple to read. It's the checker stage, the semantic checking stage, which is the most complicated because Odin has some weird rules just because it feels correct. And this is the thing when you're designing a language, is that certain things will feel correct and certain things won't. And some things will not. if he's coming on. Okay, so I'm just going to take a little break just so I can have a drink for like, I don't know, a minute or two. So I'll let people catch up. Okie dokes. So this should be okay. And we're now going to go on to the once and all. Oh, someone's asking, your colour scheme preference seemed to have changed to a more basic old one. Any reason, particular reason? So my old one was the Iridis one. I don't think it's actually downloaded actually on this machine at the moment. But yeah, I had another one. I went for this more basic one just because I can. I've been using this for about 2 years now. Yeah, about 2 years. Just because I could. I think I just wanted to just change of scenery. That was literally it. Not because I didn't like my previous one. I just changed it. That was it. And I'm using Fresh Cut by Dale Reason. It's the contrast one, and it's the one that's actually like, all in lowercase. It's a very weird one I like. I'm kind of funny when it comes to colour schemes. I don't like the default ones that everyone likes. I'm like, they're a bit not nice actually to look at. They're all very pretty, but they're not very good to work in, to be honest with you. And for instance, this is pure black, this background is, and it works lovely on my eyes. Either that or I want pure white. It's whatever reasons. Hopefully that's answered your question. So let's get onto the checker and get these files up. There's actually loads of files, but let's just get them clear first. I've got huge text, but it's probably okay. So we go close that, get that. Okay, done. Yeah, I think it's probably easier to show logic than the data structures here. Okay. So we are now talking about the checker. So this is the semantic checker stage. It's, if we remember from our little diagram, it was the end thing of the front end. This is the thing that does most of the work, pretty much all the complicated bits of the work, really. Other than the optimizer, this is the good old fun in the compiler. And the most complicated bit, because this defines the rules for the language. It doesn't define the grammar or the syntax. It is the literal rules make sense, the semantic sense, not the syntactical sense. Okay, so in here we have, in the checker.cpp file, we have the checked parsed files procedure, and this is one right at the bottom of this file. Usually I have a convention where the procedure right at the end of the file is the one that that file kind of deals with. So it's kind of my little convention. It's just, okay, I just hit the page down button or the end button or whatever. Usually whatever I need to do to get to the bottom of the file, and it'll be there. I can't remember. It's weird how you actually know shortcuts, but you don't know them until you know them. I type them, you just don't know how to speak them. It's like, oh, I realised that. It's good fun. So the first thing that you do here is you need to map all of the file paths to scopes. So you need to get some scopes ready for the packages. So each package will have a scope, and you need to assign them that way. And you also need to assign a full path to that scope and assign it to a package. So it's a nice map. You need to go from a string to a package. That's all you need to do. So that's the fun. And then you build up some of the symbol tables in the checker info. So the checker info is a big symbol tables of different things that you need to have in the compiler. I could probably reduce it a little bit more, but it's very useful to have it in the way I've done. So the first stage in the Odin compiler is I collect all of the file scope entities. So these are all the declarations at the file scope. So if we look at our little demo file again, we notice that there's an import declaration here, there's a value declaration here, another value declaration, another value, another value, another value. But technically, we know they're all procedures, so we can actually shortcut on that as well. Procedure, procedure, procedure. There's a variable declaration here because we've got the equals sign. another procedure, another procedure, another procedure, another procedure, another procedure, so on and so forth. And we keep going down this list, and we just keep collecting them one by one. We've got a when statement. We collect them and then defer that because we need to go that on the second pass through. We need to go through that if that thing's correct. This is a multiple pass compiler, and it's done that so everything is out of order. And then that's all the collection. So that's pretty much how the collection would work. So we go back to the checker. That's what we're collecting. We're collecting every single entity in a scope. So we go through each file and collecting it, creating a scope of the file and then collecting the entities. So if we go to the checker CVP here and check collect entities, this is what we're doing. We are going through the nodes in the list, getting a declaration. We need to check see if it's not a declaration or a when statement. We know then it's an error, except in the case that it could be a directive call, and we will allow that. And the directive calls, we then add this to the delayed directives. So these get checked after everything else. So like, for instance, if you want to hash assert, which is a compile time assert, you pretty much want to check that after everything else has been checked. So yeah, just delay that. Otherwise, if everything is fine, we go through it all. If it's a bad declaration, like it's a parsing error or something, and it didn't catch, that's just a sanity check in my opinion, just fine. When statements, we will leave them until later because they need to be checked on the second pass through because we need to collect all the entities first before we can even check the when statement because everything's out of order. Value declarations, which is like colon equals or colon colon, we just collect them. Import declarations, we collect them. And what we do with the import declarations is we delay them. So we collect everything else first and then we check the imports. And this was done originally because I supported using import, and you cannot just do it using import straight away because you need to make sure you've collected everything in the files before you've actually done the imports. Now, if I get rid of using import entirely rather than just deprecate it, you can actually do a hell of a lot more. You can just import it straight away and be done. So it actually makes them simplified. Doesn't make a difference really. Code's fine. Foreign declarations here. We do that here as well. And again, a foreign import declaration do this. We don't delay them because they have no relation to inside the code base. They're all foreign, so we can check them straight away. Foreign block, we just deal with that. And then anything else, we just say, look, only declarations are allowed at the file scope. Simple enough. And then we go, once we've gone through that entire loop, we then go through, we need to see if we do collect the delayed declarations. For instance, many of them could be delayed. And then we need to go open up those when statements again. So we go through the list and go, right, we haven't done the when statements, but we've collected all the entities and we evaluate the when statements. So we are doing I can never remember what the term is, lazy or eager evaluation, but as soon as we've collected stuff, we can then actually evaluate them anytime we need. So if we look at our example in the demo file again, and we look for this when statement, if this declaration here has been declared elsewhere but it's not been evaluated yet, as soon as we try and evaluate it, it will be checked straight away, and that's absolutely fine. So that's kind of how the when statement works. It's very simple, just goes straight through and just evaluates everything. It's very lazy, and this stage could probably be delayed even further, to be honest with you. I probably should delay it even further after all the collections of everything in a file and do it that way. Unfortunately, that will not. It's not the best way. Again, it's very difficult to get these things working with the when statements when everything is out of order because you've got a lot of indeterminacy going on. If that makes sense, okay. That makes sense here. So that's kind of just collecting the global entities. So if we go back to our checker stage and we go to the next stage, after that, we check all of the import declarations because if we've got everything else checked correctly, we then want to check the import entities, and then we want to stitch them up, including the using imports. Fine. Now, once everything is collected, everything in the compiler is collected, we can then check the global entities. So we can check all the global entities. And then all we do is we go list through all of the entities that we've added, which is those entities have been added to a big table, a big array, and we just go through them linearly, and then we check them. That's it. Now, these have to be checked in orders. They cannot be multi-threaded. I'll explain the only bit in the compiler, the semantic stage, that could be multi-threaded, but I haven't multi-threaded for quite a lot of reasons, actually. But this is the one stage where it could be multi-threaded. But everything else has to be checked. So if we've got a single entity declaration here, we can then check it. So what we do is we get through our entity, and we've got the declaration info as well. So the declaration info, if we just get the declar info, the declar info contains different information. For instance, if it's got a parent declaration info, this is only useful for nested procedure literals. Like procedure literal, these are anonymous procedures. The scope of that declaration, the entity it's associated with, so the entity can associate, it's got a nice little back and forth going on, like so. We have information such as the type expression, the initial expression, any attributes on this declaration, if it's procedure literal, if it has got a generated procedure type which is pre-calculated, and if it has got a using applied to it. These declaration information also store all the dependencies that this thing has. So this declaration may have loads of different dependencies of different entities, and that's used for the minimal dependency graph later on. We also have type information dependencies. This is again for the minimal dependency graph for the type information. And then this also has a big list of any, if it may not be used, but any of the labels within like a procedure. And we only want, they all have to be unique, of course. So that's fourth, and we check the entities. So now we're going to talk about what an entity is. So an entity is a named declaration within the program. Some people call these symbols, some people call them objects. I've called them entities because it's a good enough name. It's an entity. It's like a whatever. And these are the main different type of entities in the language. We have an invalid entity. Obviously, if there's something gone wrong or it's not actually meant to be an entity, say it's invalid. We have constant entities. We have variable entities. We have type names. These are type declarations, so named types. Procedures, a procedure group, a built-in import name, library name, nil, and label. So these are all the different entity groups. Now, if I was doing a very Pascal-like language, which Odin was originally, and this is where actually this comes back from it, but it's quite a nice way of dealing with things anyway, you would actually have a qualifier keyword for each of these entity declarations. So you would have a const, or a var, or a type, or a proc, or an import, or a label for each of these different types of declarations. And that's what that would be reflecting. And that's why those languages have them, because they are a one-to-one direct for what the actual compiler would be dealing with. But in Odin, we don't need to have all of them. Like, for instance, all those can be exactly the same, because they're all value declarations in my book. And they're just described differently as their expressions are slightly different. For instance, this is a constant expression. This is a variable. This is a runtime expression. This is a type expression. This is a procedure expression. This is a procedure group expression. And they're all expressions. These on the end here, these are not. These have completely different syntax, and the different syntax on purpose. This one is the nil expression. It's a very special entity type. It's just so you can have it nil. And labels are for when you have labeled blocks, and they've just got named things. Again, it's a name, so it's got to have an entity associated with it. There's many different flags for an entity here. They all do cool stuff. And then he got the entity. This entity is a huge data structure. It's a big boy. And it's got different things in it. Again, it's a tagged union. You may notice I like tagged unions quite a lot. And that's actually, for this particular reason, it's actually not because of allocating. It's because you can actually, I want to modify what the entity is sometimes on the fly. So for instance, I patch it, and it's a good way of tricking the compiler. Like I can pretend it's a constant, and then I may find out later it's actually something else, so I need to patch it to be something else. So in another compiler, you may have to reset all the pointers, but for me, I'm like, oh no, the pointers are the same. Just overwrite the union memory and everything's honky-dory. It's a nice little trick. I love tagged unions for that case. But yeah, the entity data structure has a lot of information. It has like the entity kind, which we've defined, flags, the IDs, state. Entity state tells you if it has been unresolved, it's in progress of being resolved, because it could be checked being ready, or resolved. So then you've got those three states. We have a token for the entity. So if you want to get the name, that is what it's stored as. So if you need to get the name of the entity, you usually have to go entity token string, and that's it. Entity token string will give you the name of the entity. It may seem like, why don't you just have a string for the name? And that's like almost an old legacy thing, but also the token encodes the position of where the entity was defined. It's very useful to have, especially for debugging purposes. This also defines the scope that the entity belongs to, because each scope pretty much is just a map of a name to an entity. That's all a scope is. Wonderful. We have a type of this entity. Virtually every entity has a type associated with it. We have an identifier, which is not always associated because it could be an entity that's created by the compiler, not by the user. The associated declaration information and the parent declaration information. Associated file for this entity and the associated package. So a lot of these here are actually just helper pointers, and they're probably not needed, but they're also just helps things so you don't have to look in a hash table. It's just quicker to look for it. It is a hell of a lot quicker to do a double pointer indirection than it is to look in a hash table in this case. Okay. This thing here is, I still got to do. That to do is probably like 2 or 3 years old at this rate. It's fine. I actually don't mind this approach. These are for doing the using things, because I generate new like alias entities, do all the using crap in Odin. This is new stuff that I've added for the new Odin backend, just makes things easier to deal with. And then you have order and source, which is, it's to help things sorting when you're doing what's it called? When you've got variable declarations at the file scope, they're all out of order, so you now need to figure out what order things are meant to go in. Now, if it doesn't matter what order things go in, you actually just say define them by order source. So that's what, it's just a sorting function. So that's kind of how things are going on. And welcome, Martin, to the stream. It's a long time no see. How are you doing? Oh, I'm just explaining how the Odin compiler works. I'm going very, very like skin deep over it because it is quite a big code base. But I'm just trying to explain what things are going on. Hopefully that makes sense. Okie dokes. So you can see what all the entity has, and it has different information for each entity. Like the constant has an exact value. Variables have all of this nonsense. A lot of these can be turned into flags. I do need to do later, but it's not really a problem at the moment. Type names will have all the different things on it. Same with the procedure. Procedure groups, which is an array built in, which just have an ID. Import names, nil structure, a type label, and a label. Pretty simple. And that's pretty much what an entity is. And that's pretty much what this global check thing is. Because then it takes the expression of that entity is, and it will check it and actually resolve it and what it should be. So that's all very simple, and it does all that's fine. The special bit is actually how procedure bodies are checked. So I'll explain what goes on here. As once you've checked all of the global entities, the first thing I need to do is init the preload. So this is the old little, it's a little hack, but it's just to get some bootstrapping in the compiler. So if I go to the init preload, init preload has these different functions in here, just to make it clear. You have init the core type information, so most programs will require some basic type information in it, even though it's just to finalize everything else, just to set it all up. It may not, a program may never use like any or type ID. It just sets things up so it can. The next one is setting up the memory allocator. So what this means is that in the runtime, we define what the allocator is, and we make sure that's set up correctly. We set up the context, we set up the core source code location, and we set up the map type. So these are all wonderful things that are going on. So this is just setting up, it's just the bootstrapping thing, just so I don't have to keep writing everything manually in the compiler. People can just look at the source code and say, oh, that's how it's defined. Great, done. So now we can go on to the actual complicated bit, if that wasn't complicated already. And this is the meat and potatoes of the thing, which is actually the expressions and the statements and all the direct declarations within procedure bodies. So when I'm checking a procedure declaration, I actually delete all their bodies and add them to another queue for stuff to be worked on. And the reason why I do this is for the plain reason is just because you theoretically could multi-thread it in the future if you wanted to, but there's other reasons. So yes, Martin, you had a question. Please ask away. This is, it's not very formal. This is just ask questions away. Okay, so the first question is, have you thought about having nil typed? So nil is untyped at the moment, and the reason why is because multiple different types can be nil. So such as the unions or the enums or the pointers, these can all be nil, have nil values to them. And we are reusing that 0 value across them. So it makes sense to make that untyped and can only ever be untyped. You can never really have a typed nil, in my opinion. It doesn't make much sense. What's the size of an entity? It's quite huge, to be honest with you. I think it's a huge data structure. I really kind of, in some regards, it's not nice that it's huge. I can find out what it is for you if you want. Just do a little hack here. That's what I normally do. If true, return 1. GB print. I'm just going to write size of entity just for you. GB size of entity. Yeah, the entity data structure is, whoops, taking a while, 328 bytes. It's huge, and I could probably make it a hell of a lot smaller. There's just probably a little bit too much date information on there for the time being. But yeah, I think if I can get it to 256, I'll be quite happy. Like, for instance, there's some extraneous balls everywhere, which could be... But yeah, again, people call it entity or symbol or symb or object or whatever. But yeah, this entity isn't the same as an abstract syntax node. It's just it relates to a node, so you can look up the extra information for it. Because I store loads of information on this. This isn't actually the node. I mean, it's just I've called it something else. Does that make any sense? So yeah, the entity is huge. It's a big boy. It's a big boy of a data structure. For instance, if I go back, the AST node itself, how big is the AST node? Did I get a typo in there? Is it just... Oh, it's AST. Oh, sorry, I've got the wrong coding style. AST... Is it just AST? It's just AST. I don't know. I've been writing another compiler. The AST itself is huge as well. It's 368 bytes. That is massive. Now, on average, that is twice as big as it needs to be. I know this from profiling the code, and it could be, again, half the size. But I do have it for the plain reason it is so much easier to do when you're cloning a node. You just mem copy it. Technically mem move. I always use mem move, and it's done. Yeah, but sometimes the biggest data structures like that are huge. So yes, there's going to be loads of cache misses. I can't say that word. All over the place. So yeah, that's kind of crap. So we go back to the checker, and what we do is here. So as I was saying, when I collect the procedure declarations, I check the signature, which is the type of the procedure first, and only the signature. I don't collect the bodies. And I only collect the bodies of ones that are like defined, like completely specialized. Like, for instance, parametric polymorphic procedures or parapoly procs. They may not have a well specialized function body, so we don't actually check them. They don't get added to the stack to check. So these are the procs to check, and this list just keeps on growing, in fact. So in this list, we will just check it, and you get the proc information here, and then they'll go from the list. Now, the proc thing here is you get the body, you make sure everything's correct, and you set it all up. If it is procedure or polymerized, you just say, look, it's an unspecialized procedure, and just error out. It should never get to this stage, but it may do. This is an old comment. It was never used. Don't check. Like, it should never have been used, but just, yeah, whatever. And then we do the check, and then we check procedure body. So we go to that procedure now, and we can then check the procedure body. So someone's asking, you did well picking so many names for things that are almost ineffable. A lot of these names are very common if you're used to writing compilers. That's half the problem. If you're not used to writing compilers, then they will be completely unknown to people, and that's hot. It's just one of those things that if you know compilers, then the names make perfect sense. If you don't, then they seem completely random. So yeah, it's one of those where if you've done it before a million times, you get used to it. And I know that's not nice for beginners. I really know that. But there's not much you can do, to be honest with you. But yeah, so you got the check procedure body here. So we'll check proc body. In this case, we check to see if it's a block statement. And then we go through the entire procedure body and just check each statement as it goes along. Because procedure bodies are made up of statements. And a declaration is technically a form of statement. If you think of it that way, it's a special form of statement. So yeah, it's just specialization of a statement that does stuff. It's weird, whatever. So then we go through all the list here of, this is all the parameters in here. So we check all the parameters and stuff. And there may be also usings on parameters. And if there are usings, we add those to the using entities. And then we add them to the list of the using entities. And then we just add them and go along. And we need to check before we insert them, there are any namespace collisions. So that's kind of thing with using and stuff. So that's when you have using on parameters in a body. It just adds it to the scope. So it's all lovely. If there is a where clause on a procedure, this is like for this works for any procedure, by the way, not just parametric morphic. It just can be a sanity check yourself. They get evaluated after you've done everything else for a few reasons. So if it fails, the body never gets checked. So even though the body may have been cloned, it doesn't get checked because it's failed. So this is technically a waste of memory. I don't call it a leak because compilers don't ever leak in that regard. The way I design Odin is that you allocate memory and you're pretty much never free. It's a very good way of strategy of doing compilers, in fact, because they usually run once programs and they're just extremely linear and you need all the state at all times. So you don't want to, the only time you want to kind of free stuff is when you're resizing arrays, and that's about it, and resizing hash tables, like those two data structures. That's it. You don't need to free data usually, like unless it's like very temporary, and even then you can use custom allocators to help that. But yeah, so once you've got through all this stage, you go through here. Now I say don't err because I should have checked the erring beforehand. I just do it anyway, so it's just to clear things up. And then we just check the statement list. So this is different things. So if I open up the different things on the side here, unfortunately they'll be very small on this monitor for you to see. So I'll just kind of describe them. In the source directory, so the src directory in the Odin code, there are many different files and many of them are very long. Some people have said, how can you deal with a file that is 10,000 lines long? And the short answer is quite easily if you've got a decent text editor that can just go, right, where's the function that I need? Oh, I want to go to check, selector. There you go, it's there straight away. And you can just browse the entire code with your text editor if you know everything that's in there. In my opinion, the size of a file is very little of an issue. If the file was 20,000 line longs, it would get a little bit more difficult, but it's not really that much. The text editor will be fine. So that's the case. So yeah. So in the code here, you'll see that anything that's pretty much starts with the word check, like check decal, check expression, check statement, check type, checker, check built-in procs, these are all associated with the checker system. Very good name in that regard. Parser is just called parser. It's technically two files, a header file and a source file. The tokenizer is just one file. Specific data structures. I'm slurring my speech because I'm going to sleep soon. I apologize for that. I'm just very tired. It is nearly midnight here. So Twitch did not kick me off. I just could not get on Twitch. There's something wrong with Twitch. That's my problem. I have no idea why. I was using Twitch before, and I thought, I'll try YouTube Live the other day. And I I did it the other week. People didn't really like it and wanted me to go to Twitch. Now I can't get back on Twitch. I have no idea why. So, yeah, I'm on YouTube Live. It's fine. Again, it's not as much views as I normally have or anything like that, but it seems to be okay. It seems to be working fine. So I use YouTube Live. No problem there. But yeah, so there's different files in here, and you can see. For instance, there are general files all scattered over the place. For instance, the entity file, which again defines the entities, stuff like that. There'll be the exact value file, which defines the exact values and stuff, and so on and so forth. So there's many. And there's a lot. Again, a lot of these files in here are just me defining data structures, like as a hash map, or a pointer set, or a range cache, or a string set, or a string map, or a thread pool, or a big int. Again, loads of these are data structures that I needed to define, and so forth. So this is kind of a very, very high overview of the Odin compiler, of the front end at least. And if anyone has any more questions, please ask. I do not mind answering questions. So please ask away. But yeah, so the general idea is that this is kind of how it all works. So it kind of breaks it up. Now, if anyone wanted to come maintain it, if they want to do work on more of the middle end rather than just the front end, they will need to know the front end, unfortunately, because I kind of rely heavily on a lot of this stuff. For instance, there's a lot of little macros. So a good example of this would be in check statement. And when I go to the check statement internal, because I have a check statement and check statement external, which is the check statement wraps the internal and does a lot of state checking for reasons. You'll notice I have a lot of these switch statements which have a case AST node on them. And the reason for this design is a case AST node is this here is a pointer to the AST of this type, and it passes in the node that I did in here. And each node case is ended in a case end, which does thing. So what this does, it creates a new scope for me. It creates the new thing here, and so on and so forth. This is kind of what I do in Odin with the switch-ins. And it does that, but this is kind of my hack to get it working in C. Again, people may not realize, but a lot of the reasons why I designed Odin is actually just because of the issues I had with C. And I wanted to get around those issues by implementing them the issues I had with C, implementing them in Odin. So that's kind of the way I did it. So for instance, let's look at this general example here for a statement. We check for an expression statement. We check the expression base, which does some error handling itself, by the way. All these there's loads of error handling throughout the entire thing. Some people complain about error messages, and yeah, I agree with them sometimes. Sometimes you just cannot know. Like, it's like, yeah, sorry, it's the best error message it's going to get, because it's the most weirdest, like, it's so obscure it doesn't actually have enough information to know why. Sometimes it does, and I've just not written a very good error message. So please complain about them. Please, really, really complain. I'll get better error messages that way. So we're doing the expression stuff here. We're passing expression. So, right, okay, so this is a good thing to understand now in the compiler. So when you're passing expressions in the language, I have a thing called an operand that you pass in. So this is an in-out parameter. This is not an in or an out. It's an in-out, so it can modify as it goes along. This is the weird thing about it. So the operand, if I just click on one, which is defined in the checker file, has loads of information in it. So many different compilers have certain things as well. I remember I was speaking to Per Voinson, who was doing Bitwise and many other things. Very cool chap. Check his Bitwise project out, which is a bit dead. It's dead now, but I'd still recommend checking it out. We were just talking about this, and I didn't realise, oh, you call it operand too? And he says, yeah, because we probably just learnt from the same sources. and stuff like that. So we just call, I'm going to find out, which is, yeah, it's called an operand. So the operand is kind of an intermediate value. So whilst I check, so it stores all the addressing modes, the types, the values, the expressions, the procedure IDs, and entity groups. So it's the thing you just pass along. It's really useful to have. So Martin's got a question. This might be fading my knowledge of Odin, but do we have type coercion promotion in Odin? The answer is no. Odin is a very type distinct language. This is a term I made up because strong typing is not enough for a term. For instance, the Zig language, that Andrew Kelly was on the chat earlier. Zig is technically a strongly typed language, but there is a lot of type coercion promotion going on. So strongness doesn't mean distinctness, is what I call it. So in Odin, just to make it very, very clear, let's look at the distinct. That's an awful example of distinct. These are all dreadful examples of distinct. So let's just write up a file here and get a new font. So sets index Odin. Let's say the common go-to example I always do is, let's call it an int alias. Oops, alias. Like so. So in C and stuff, you could do this. And if you got int alias, this would be allowed. That is perfectly fine in Odin, because this is an alias. Just now you've got naming a constant. This int constant's a type, so it works. But in Odin, we allow distinct types as well. So we could call this myint, and we say this is now defined as a distinct integer. So it has the same memory layout as an integer, but it is completely distinct from its type. So if I said int 123, and then I had, just do it again, we had myint, and we assign that x, this would be an error because these are distinct different types. So another way of expressing this is if you had a static assertion, int alias is exactly the same as int. But in this case, myint does not equal int. Now this is completely different to C's typedef, where C's typedef acts as an alias, but in Odin, things are distinct. And this is an extremely useful thing to have, because type distinctness doesn't just have with distinct. In Odin, int could be the same size as could be as that. Let's say on 64-bit platforms, yeah. But int and i64 are completely different types. So even if they represent the same amount of memory and data, they are semantically different types. So you will require an explicit cast between them to convert the type conversions. Is that clear? This may sound like you need to do loads of casts everywhere in Odin. And the answer is you don't, because of how the type system works. And that's the pure magic of how it works. Is the constant exact value system that I came up with, which is partially borrowed from Go, to be honest with you. Again, I'm not going to blame it. There's loads of things in Odin that I nicked because it doesn't work. It was just because it was a very good way of doing things. So Martin's got a follow-up question. He says, I'm just going to type out what he's written, so for other people to see. For instance, okay, say I've got this C code here, and then he's wrote auto, well, I'm just going to write auto here, C plus A plus B. How does Odin deal with this? It doesn't. It says it's an error. It says it cannot because A and B are different types. Full stop. That's it. It's an error. They are complete distinct types. There is no type coercion whatsoever. So what you would have to do here in Odin is, let's say we've got the same thing going on. Whatever. That. So we have U8 equals 1. B, let's say it's an I32 for the time being, equals 2. C in this case, this would be an error unless you explicitly went, okay, that's an I32. Or say that's C0, that's C1. Or we said this. Yeah? So unless we did an explicit cast type conversion, you could not get them across. Is that clear as well? So Go has a very similar thing as well, and so many other languages like have this type distinctness. Again, I came up with the term because it was the best way of describing this type distinctness going on. Does that make sense to most people? Yes? No? Maybe? I don't know. Can you repeat the question? Yeah. Hopefully that makes sense. So to get this to feel correct, especially with constants in language, it was a little bit more work. So I'll explain what goes on. So if let's say I have a constant here, let's say I have this constant here, which says foo, and it says 1, 2, 3. Now, a constant, which again has these two colons here, technically you can have as many spaces in between them as you want, but conventionally I don't have any, if I don't have a type in there. This is a constant named foo with a value of 1, 2, 3. Notice I didn't say what its type was, because its type is untyped integer. Yes, you have a type called untyped integer. So this now brings us to the other part of the compiler, which is their types. So I'm just going to the type data structure at the bottom here. So in Odin, we have different types of types, or different varieties or kinds of types. And if we look at the different kinds of types, we notice we've got this pattern of an enum again, this union. Notice I keep using discriminated unions everywhere, and C doesn't support them very well. But Pascal did, and that's languages from the 70s. Oh, that's great, isn't it? How languages from even before C really had it, but C didn't. I understand why, but still. So in Odin we have different types, and we have different categories of them. So we have basic types, which are the ones that are built into the language. So there's a big list of them here, like booleans, integers, rune, floats, complex quaternions, size-specific types like integers, pointers, strings, any, type ID, endian-specific types, and then the untyped types. I didn't know of a good name to call them. It just sounded better with untyped. So let's go with that. And then after that, I have aliases as well. Like, for instance, by default, I have an alias called byte, which is just a U8, but I call it that. Then we have all the different types. We have named types. Now, named types are distinct, of course, and they have an associated entity with them, and they have a base type and a name. Again, they're distinct. We have generic types, which are for parametric polymorphism. Pointer types, which have an element type. An opaque type, which is an element. Opaques are weird. I won't explain them yet. Most people don't understand what they mean, but it's not the same as like a C's opaque type. Odin's opaque types are pretty much like, hey, look, it has a base type, it has this memory layout, but they're opaque, so you can't really do anything to them. They are weird things, but they solve a certain problem I was trying to solve at the end of the day. If that makes any sense. We have array types, which is nice. Enumerated arrays, which is a cool feature in Odin. Not many languages have enumerated arrays. It is actually an old feature from Pascal, again, I nicked. But it's a damn useful one. Oops, sorry, just getting a drink. Like so. We have slice types again, and we have dynamic array types. We have a map type, and the map type has a lot of crap in it. They're all different types, like the key value, the value, and then the generated stuff on top. And we have a struct type, a union type, the enum type, a tuple type. So this is actually a nice little trick that I have in the Odin compiler, is that in procedure return values and procedure inputs, like the parameters and the results, they are treated as if they are tuples. So Odin doesn't have, so the short answer is Odin does not have first-class support for tuples. So the user cannot write a tuple. And the main reason for this is I think you should never need to have a write a tuple in a first-class support. They are not useful. They're not what you want. They're not any of that nonsense. So in that regard, you don't want them. But you think, okay, I do want them in some cases. I'm like, no, you want a struct in that case. You really just want a struct. So why does the Odin compiler support tuples internally as second-class citizens? Not first-class citizens, but second-class. And it's mainly for mortal return values. And so what that means is you can have these be automatically destructing tuples when you're returning them. It's a very weird thing I came around, but it makes a lot of sense. to get there. So tuples are effectively like a weird struct at the end of the day, but all the fields, none of the fields are named, and you can do whatever the hell you want with them. Now, there's extra parameters on here. For instance, those parameters are effectively just for the back end. So they know where they can treat it as it, or the middle end technically, but treat it as if it was just a struct. But technically, it's just a tuple is just a list of types, and that's all it is. And then you use it for the multiple return values. It's a very nice little trick, and you can do a lot of cool tricks treating them as if they were internal tuples. We've got procedure types, bit field types, and they've got a special one with the bit field values, which are bits. Now, if you're using a language like Zig, this bit field value thing would be the same as the arbitrary integers, but in Odin we don't ever want them for numerous reasons, so I only kept them to be in the bit fields. And this is because bit fields are weird things, and I still haven't figured out all the rules. Again, I love a lot of people support from other people about better ideas for them, but bit fields are the hackiest things in the world. So yeah. The next bit is the bit set type, which is, again, I love this thing, nicked from Pascal again as well. But bit set is you set an enum or a range, and you can just set the bits like that. Oh, it's a wonderful thing. It's much better than doing the old C approach. And then the last data type in here is the SIMD vector, and so forth. So hopefully this is all coming along nicely to people, and people are understanding this. So hopefully, this is making sense to people. So someone's asking and says, I don't like tuples either. My language only has a tuple, so I mean like a duple and a triple. One reason is pattern matching, casing, switching. You can match 2 or 3 values at the same time. So yeah, I'm not a big fan of pattern matching either. But the reason why I'm not a big fan of pattern matching is because I don't think it's useful most of the time. Which may sound, of course it's useful. I can see in many cases in my language or this use, it actually is useful. It highly depends on the type system. So it makes sense if your discriminated unions in your language are kind of an extension of an enumeration with different fields. So an example of this would be like Rust, where their discriminated unions are an extension of an enum, and you have different fields in an enum, and then those fields have different parameters to them. So in that case, it makes perfect sense for having pattern matching, because you want to be able to get the parameters within the named enumerated fields. That's such a horrible way of explaining, but that's how it works. In Odin, though, discriminated unions are hell of a lot simpler, and in fact I think they're probably the simplest I've seen in any other language from a type system standpoint. In fact, they're not enumerations by any stretch of the imagination, but because they don't need to be named, and they take advantage of Odin's distinct typeness, like it works in that regard. Because many people say, so how am I supposed to have things with the same type, but I want to have different names? I'm like, well, you just have a different type with a distinctness to it. And it's like, oh, that solves the problem. Like, yeah, it does. I think Odin's approach is honestly is unique, but it made perfect sense when I was designing it, and it just naturally fell out. Don't worry about someone about nagging about pattern matching. But yeah, seriously, it's pattern matching is just something that only makes sense if the type system actually allows for it. If the type system doesn't even allow for it, it doesn't make any sense. It's like requesting a feature. It's like saying, great, I need some coal for my car, which takes petroleum. It makes no sense as a question. It's like you're requesting a feature. It makes no sense. But I don't mean that in a bad sense. Please do not take that as an insult. It's just that sometimes you have to... yeah. So by the way, the only reason I have line numbers enabled is I very rarely use them. It's just I've been using them for something else. So when I'm like doing streams for people, not just for like at work, they like line numbers. So that's the reason why I have line numbers. But yeah. So back to the pattern matching. It only makes sense if your type system allows it, is the short answer of it. Because if I look for the union type in Odin here, You'll notice union type. I just have a list of the types that union can be. None of them are named. None of them have parameters or arguments to them. They're just types. So there's no need to have literally at all have any pattern matching. You just treat them as a basic switch statement with a basic case, and it will work. You can do basic type assertions like that, and it will work. There is no requirement for this to have type matching. So pattern matching, I mean. So does that make sense, people? Hopefully this makes sense. It's not, I'm saying pattern matching is a bad thing, really. I'm just saying it makes no sense for Odin. So when people request features, be careful how it works with the rest of the language, because you may not have actually thought it through correctly. Even myself, I wanted, I'll have this feature, and then wait a minute, that doesn't make any sense. So Martin's asked a wonderful question regarding type. So he's asking, let's say you had this C here, and you did this. Would this be an error too? And the answer is no, this is perfectly valid. And this is because of how the constant system works, and it's had to make it feel correct. So but the question is, why is this valid, and what is its type? So they're two different questions, but yeah. So the reason why this is valid is this can be evaluated at compile time. This is the number 1, and this is the number 1. What's 1 plus 1? It's 2. So the value of this expression is 2. And that's completely, it has a number. It's untyped, it's just 2. But what untyped type is it? So this on its own is an untyped integer. This on its own is an untyped float. So if you add them both together, it'll be an untyped float again. Even though even internally it may be stored as an integer, like just 2, it is actually just an untyped float. And the default type, the default type for an untyped float is an F64. Sorry, it's an X64. So that means sorry. So this 1 and the 1 0, this is actually, that's how the value to, and the type will be F64. So this is actually the equivalent of writing this. So those are equivalent. But the question is, this be allowed? And theoretically, I could write this, and that would be allowed, because the constant value on the side is 2. This is just 2. And you may be really confused, like, why is that the case? But the thing is, it feels correct. When you're doing constants, you just think, well, it's the number 2. It should work, right? And it does. So type promotion does work. But the thing is, it's not type promotion. You say, so type promotion works with untyped. It isn't type promotion, though, technically. It's just value promotion. That's a number. These are numbers. They have got not a type. They're not really a type associated with them. They're just numbers. They're treated as numbers. So yes, there is type promotion with untypedness, and that's where the type promotion goes, but untyped, again, not typed. So welcome to my little loophole, getting around the problem of type distinctness by just not having types. It works. And it's a wonderful trick, and it works perfectly. This took forever to get actually work correctly, and not work correctly, but to make it feel correct. Again, a lot of Odin is actually making it feel correct. So things may not be technically correct or technically simple or structured correctly. And you'll see many hacks in the compiler. And they're there usually because actually that felt correct when you're actually using the language. And that might sound like a very awful metric, but it was more like I can define it correctly, but yeah. Yes, so in your language, yes. So Andrew's saying you might say the value gets special treatment when the value is comp time known, and that's correct, yes. So if it's compile time known, this value, it'll get special treatment. But the thing is, it's not special treatment. Is that untypedness means it hasn't got a type, but it means it could have a default type if there's no type specified. That's the thing, that it needs to have a type. But the value itself means it has it defined itself. So so the value is constant. It's evaluated as the number 2. So the 2 can be represented by an i30, an int, or a float. Absolutely wonderful. So someone's asking, does the same with this. So if you had 1.2, D of 1, and then C was C plus D, would that work? And the answer is yes, this would work as well, because this thing would be evaluated to the value of 2.2. But that means then this type would actually be the default type, or whatever an untyped float is, which is an F64. It may seem like a very weird thing, but it feels perfectly sane. Someone's asking, I wonder how this feels in a math-heavy application. It feels absolutely wonderful, because Odin also supports array programming. So Odin's been used in very math-heavy applications. One professional commercial application at the moment is Embergen, which is a real-time fluid simulation, which uses Odin as its programming language, and it uses maths everywhere, and it absolutely takes advantage of many of the things in Odin, and it makes it, it feels lovely to use. So you can make Odin feel like a very high-level language, but it isn't. It's extremely low-level at the same time. In fact, it's lower level than C in some cases, but higher level in others. If that makes any sense. So the plan is I'm not updating untyped floats to a 128-bit float. I'm going to actually just properly have a big number library in this language. So when you're designing big number libraries, you pretty much want a big. So these are big number library. What you want is you'll need a big natural. You want a big int, big rational, and a big real, or you can call it a big float. And these need to be completely arbitrarily big. But the problem is, if I'm defining the specification of a language, I might just say what a minimum requirement is. And I may just say integers must be a minimum, allow up to a minimum of probably like 256 bits or 512 bits of information. I think that's probably more than enough for the specification for most compilers. So if they don't have arbitrarily big, they'll have to do that. So you're saying, what about square roots of sines, cosine, other math functions for them? So the answer is they will not be supported at compile time, because the compile time operations are very trivial, but they have to be trivial on purpose. So compile time execution in Odin doesn't really exist in the same way it would do in Zig. So in Zig you have like full-on like semantic macros, as I call them. I don't know what like comp time funds in Zig. So yes, someone's asking, natural numbers could not be negative. That's correct. So natural number is 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever. So the reason why you separate them when you're making big number libraries is because negative numbers are a pain in the bum. They are quite difficult to actually do things correctly. So natural numbers are lovely. You can do addition, everything fine. Negative numbers are a pain to do things correctly. Rationals are, again, a rational at the end of the day is just it's just two big ints, and then a float is a bit more complicated. So a float is effectively, you've got sine. So now actually you got a big int plus a big int again, which may sound bizarre to some people. Like, what are you talking about? How's it two big ints? Well, the reason is because you got a mantissa and an exponent, and that's it. Because natural number is the technical term for it. Yes, could call it unsigned, but no, that's just how you do it. That's how most big number libraries would define themselves. They call it a natural number. That's how I'd define it. So I don't want to change from the conventions of how the libraries do it. So that's kind of how things working in Odin for that stuff. So if people want to see the exact value thing, it's a very simple thing. It's only 1,000 lines actually for the exact number thing, plus the big int stuff, which I try to write and I never finish properly, and it's all a bit crap. Yes, it's not the best thing in the world, but it works. It works, for my uses at least. So an exact value here is quite a big, again, a big data. Oh look, there's a discriminated union again. Who'd have guessed? Now, again, reason why I discriminate units is because I can just copy them as I go along, memcopy it again. Memcopy is a wonderful thing. So in the exact value, we have different value types. So we have a boolean, a string, integer, floats, pointers, complex numbers. So these pointers here are effectively like uint pointers, not just anything else. So we have complex numbers, quaternions, compounds here. So these compounds are pointing to a structure, which have like a compound literal. Procedures here are just like procedure values, like procedure literals. And then this is a type ID, which I store as a type. So talking to Andrew on the chat there, Andrew Kelly is the creator of the Zig language. Zig, I know, has comp time ints and comp time floats. One thing, again, this is my minor criticism of Zig, is one, I recommend you'll need a comp time boolean, really. Even though technically a boolean in Zig is technically an integer, it would be useful to have it as a different type, in my opinion. And you could easily, and also I'd recommend adding not just comp time one, but just actually adding into the type system a string, because in Zig, if I remember, well, there's multiple different ways of actually writing it. A string in Zig is one of these different forms, etc., like that, or whatever. So that's in Zig at least. And you have all different strings, but the thing is, that's not a string. That's an array of bytes. And in Odin, we make a very distinct difference between this, between an array of bytes and a string, because semantically they are different. So when you're dealing with it from a type system, you want to know, actually, does this represent just data, like integers, like an array of integers, or just represent array of characters? So when I do literally fumt.println and I pass in some data, I want it to behave completely differently if I passed in a string. And the only way I could do that in the type system is if I had a way of distinguishing between a slice of bytes and a string. And in Zig, I cannot do that. You cannot do that, and you make some guesses here and there, and to be honest with you, it's a little annoying. Even in C, they make a distinction. So again, sorry, I'm making a minor criticism of Zig here, Andrew. It's not really it's just a minor one anyway. Is that in C you have unsigned char, signed char, and char. So if you have pointers to all of them, well, that in Odin is technically a pointer to a U8. Technically it's whatever. But this one, there's a C string. This actually has completely different meaning. Technically, a C string in Odin is actually a const, because strings are constant, but whatever. There is different meaning there behind it all. That's fine. So someone's asking why is so Tetralux asking is why an I64 for a value pointer rather than a U64? The reason is it makes no difference at the end of the day. It literally makes no difference, especially since pointers never really use all 64 bits anyway, and not just that, they are the signedness. I assume 2's complement everywhere, so it's all fine usually, and I just kind of enforce 2 complement. But that's about it, really. I could always turn it to a U64 if I wanted to. Shouldn't make much of a difference. That's it. So yeah, so there's my distinction. So in Odin, I make these different distinctions between a string and a byte array. So hopefully this is making sense. I know it's shooting off randomly for the compiler. It's the way how my brain thinks anyway. I'm kind of like a Monte Carlo simulation. My brain is. It's all over the place. Hopefully that's okay. Hopefully I'm answering everyone's questions. Again, another talk about Zig, the Zig language. I know this is the Odin stream, and please use Odin. Please use Odin, but also try out Zig as well if you like. Maybe see which one you like. But for the Zig language, one thing with the comp time values in it, it's very limited case of the exact value system in Odin. So theoretically, you could apply it to more things. So if we wanted, as Andrew was suggesting, the square root, sine, cosine and stuff, they would all have to be built-in procedures in Odin, and completely built in, and they would have to support the exact value operations on them. But since Odin does not have that built in, and I'm not sure I'd ever want it, maybe I do, I don't know, I could be easily persuaded, to be honest with you. I don't support that yet. For instance, if I want to see the built-in procedures in Odin at the moment, here's a big long table of all of them. So Odin's ones are very simple. We'll just go to the string ones, they're easy to read. We have len and cap, which is for like array-like data structures and maps. We have the built-in, the size of, the line of, offset of all these different data structures. Choking on there then. The swizzle operation, which is do swizzling of arrays. So you can swizzle their things. It's built-in operation. It's a nice little thing. We have the... I'm not talking about it. Oh, just stop. Let's just stop for like 20 seconds. And I've got my voice back then. Ready? And it's back. There we go. So, we can now have the built-in procedures, which allow for other constant files like the complex and quaternions. We can get the real and imaginary, the J imaginary, K imaginary, and the conjugate values of the complex numbers. We have the expanded tuple. We have some lovely built-in things like min, max, absolute, and clamp. The rest are all intrinsics, and they belong to the intrinsics, built-in intrinsics package. And we have all the type-based ones as well, which are Odin's way of getting runtime type, getting compile time type information with all these lovely intrinsics. It's a bit of a hack, to be honest with you. Well, it's not a hack. They actually map directly to the procedures I use in the compiler. Like, they are pretty much one-to-one. They're exactly the same as I use. So, if the compiler can get by with it, you can probably get by with it as well. To a point. Like, a very certain point. Like, you probably want some custom ones, which would require a form of macro or form of extended function, which I won't discuss yet because I've got an idea which I might probably not implement at all, but let's not go there. So yeah, so what Andrew was discussing is, would you want some of the built-in those kind of procedures? And I could add them here, and they would have to be implemented, and they would have to work with all the exact values as well. But I'm not particularly sure I'd like that. So someone's asking, why are min and max built-in functions? And the main reason is actually it's for two reasons. One, there are such a common operation I do all of the damn time, like so common, that I kind of want them there. Like, I'm not even joking. I don't think I've never written a program that has never needed min or max, one of them at least, or an absolute. The second reason is actually a very clever one. Is because if you see this true thing here, this table column here means is this variadic, so it's allowed for multiple different parameters. And the short answer of it is you kind of want that. So in Odin, another big example of the min-max stuff, is I can do this, min 1, 2, 3, 4, 5, 6, and that will work. So that works absolutely wonderfully. And you can do that and fine. And it'll also work it very cleverly as well. So if they are constant values that are evaluated at constant time, it's like complete compile time as well. And it'll also short circuit as if it needs. So it doesn't do all the crap if it needs to. So you could not do that at user level, technically. I just love it built into the compiler. It's just one of those things that it seems a bit weird. Like the rest make perfect sense, but those seem a bit weird. I'm like, no, they're just... It's worth it and it feels right. It's one of those compromises that I just take. Someone's asking, is the swizzle usable in vector math? GLSL-like? And the answer is, it's a bit weird. So I've thought about actually supporting GLSL-like swizzling actually at the type system. And it's not that difficult to support. At least the R-value based one, not the L-value based one. The L-value GLSL is a bit crazy. And I wouldn't recommend doing that, but I'll explain one, because that's full-on broadcasting. So let's say you've got a vector, vector 4, perfect. We could do an X, another one here, and we pass in the swizzle of that vector, and we can pass in the parameters. So that does the exact same thing as you'd want. Yeah? But we could do, I'm just going to make sure it's not do that, whatever. We could swap the order of the parameters like this. We could only just have the first two. We could then just do that. We could just do all of the same first parameter, and that would work. So this is how the built-in swizzle operation works for arrays. And its syntax isn't as pretty as, let's say, GLSL. So the GLSL equivalents of all of these would be, this is not Odin code. The XYZW, WZYX, XY, ZWX, XXX, yeah? So I could support those in Odin if I wanted to and do the same thing. And Odin does actually support, as a compromise, remember, Odin code, you can do this, and that's the equivalent as doing that. This may seem really bizarre, but it actually just feels correct as well. And most people just naturally do it, which is really surprising. But people just naturally do it, and it just feels right. Odin also supports the RGB stuff, so we always support X, Y, Z, and W, up to 4 components. After that, you have to use the indices, and we also allow RGB and A. Again, it seems very weird why you'd support this, and it seems like a very a bodge, but no, again, it feels correct when using things. But the swizzle is a universal thing, because if you've got a vector which is technically let's say it's 9, or it could be thing, you'll have to use this syntax because the GLSL syntax does not make any sense anymore. Does that make sense for the person who asked the question, which was Marcus? Yeah? So this is one example of Odin's array programming. So for instance, just to explain this, is the A and B. So Odin allows you to do this. It even allows you to do this. Array programming is very powerful. Now, I don't support... there's different levels of basic linear algebra systems and type systems. So I think Odin is level... I think it's level 1. It's level 0 scale. Level 1 is vectors. Level 2 is matrix and vectors. And level 3 is vectors and matrix and matrices, yeah. So I think Odin is only level 1. I don't want to go any higher because then you have to make some memory layout decisions where you're saying, I prefer column major to row major and all that lot crap. And it's like, I think in those cases it'd be more explicit, just have your own procedures. But yeah, I understand why people want the sugar, and it might be worth it. I wouldn't allow mixing RGB and A and X, Y, and Z, W, obviously. I wouldn't allow mixing those indices, selector, field selection, whatever, sets, whatever. I can't think of a word for it, but I could allow the broadcasting. My only issue with the broadcasting is that if you have an array that has more than it was allowed, you would not allow it. So for instance, because this is in a vector 4, array 4 or something, I would not allow that because that would be going past its original size, and it's not something I want to support. But I could support just 1 or 2, and then the thing is that's the case. So in these cases, the actual type would actually become even weirder. So this is actually, unfortunately, the case with the swizzle. It has to get a different type, and it will just go with a weirdness. So this is again an edge case in Odin again. I'll put in the actual explicit types to see what goes on. So if I do call this vector 4, or let's call it vec4 to make it sound like a GSS, whatever. I make this distinct. Yeah, like so. The types for all of these are going to be as follows. And they are the types. Does that make sense? Now, the reason why is that, look, these are the same length, so they can be the same type. If it's not the same length, it'll have to be a untyped version, and it's just, they won't be untyped, these are completely typed and distinct. So if you need to cast to another, let's say cast to vector 2, you can do that. But yes, it's a weird oddity, and there's, again, it's edge cases, but there's no, unfortunately, again, designing a language, you make loads of compromises everywhere, like life. You cannot make a perfect language, ever. You just have to make compromises because humans are flawed. Humans are flawed, and we like things in different ways, and you have to deal with computers which got flaws in them, and it's like, oh great. Yeah, humans are weird things. We are weird. And we cannot, again, you cannot have everything. Scarcity exists at the end of the day. So, because we have free will, there's the answer. But yeah, so they're kind of the different things. So I'm kind of going all over the place with the checkout. I'll probably have to do another video because I want to end this in a minute or two because I've been going for over 2 hours now. I've been non-stop talking for 2 hours. But the general idea is that this is kind of the compiler, and it's going to give you like a skin level deep of what goes on. I've not talked about the middle end yet or the back end, and I've only really covered briefly the checker and all the other things. I've not gone step by step for every procedure. Like, what does this procedure do in X, Y, Z? Because that would probably take me a few weeks. Like, honestly, like weeks to explain, oh, this is what this one does. This is what this one does. But hopefully that's been good. And thank you for all been listening on this Odin stream. I'll stay around for the next 5 minutes just if anyone's got any questions. Because after that, I'll be going to sleep. Because it's quite late for me now. Because that's usually the only time I have time to do streams anyway. So thank you for watching on the day of our Lord, Odin's Day, Wednesday. And it is now Thor's Day today, which is Thursday. And praise be his son, Odin's son. And thank you for all watching. So, are there any final questions before I go? So the question is, you guess implementing the swizzle case would again make it a special case, and the answer is yes, it would. But I don't particularly mind special cases in language design. Sometimes the compromise of the special case is worth it. For instance, if I check in types.cpp, and then we look for selection, lookup field with selection, we see we've got loads of edge cases. So there are loads of edge cases you have to do with selections. Like, for instance, here, look, there's an SOA array. We also have to check for the RGB maps the XYZ, and then we look for the XYZ ones as well, which are here on here. Like quaternions have XYZ, which was a new thing I added. XYZW. The arrays will have XYZW and AB and ABC, AB, RGB and A as well. And they'll have those fields. These again edge cases. So theoretically, I could have swizzling if I needed to. I don't need to have dot operator in my opinion. I don't like an operator for dot products for any reason, to be honest with you. I think a dot product is much clearer if I wrote dot xy. Like, there is, I can't think of an operator that would go there. that would act as a dot product. Like a dot product is an inner product, then you have outer products, then you have whatever. But like again, it makes no sense to have it as an operator. Yeah, but that makes no sense because dot is for selections. So like, oh, get me the Y field of X. Yeah, it makes no sense. But yeah, this selection syntax here is the special cases for the different types. For instance, like these have, you want to access the array allocator type, which is very specific. Or it might want to, there's many other cases like basic types. You've got data and ID for any's. You can explicitly get them. Or the quaternions, you can get them explicitly as well. A specified layout there. Bit fields aren't that special. SOAs are special, of course, because they're arrays. These probably should be removed. Even though I understand why they're nice, they should be removed because there are better ways of approaching that for numerous reasons. But yeah, that's about it. So if there's any more questions, I'll wait one more minute and then I'll go to bed because I'm really that tired. There's someone saying I was slurring my speech. Yes, because I'm that tired. And I've got to work in the morning. And then I've got more work after that. Work. More work? Okay, then. I'm just going to do the sounds from Warcraft with my voice. Because I can just do about them. More work? No, more work? Okay. Yes, so just before I go, so say you could have you could have all the special cases of swizzling. I don't want the STUV, the STPR stuff. I think they're awful. So another question someone's had is, I've just tuned in, so you might have answered this already. In a previous article, you mentioned alternative backends to LLVM. So yeah, so just before I go, LLVM unfortunately is pretty much the only option if you want a optimizing backend, which also supports most of the default platforms such as AMD 64, x86, and ARM. There is no other alternative out there that has an optimizing backend. The alternative I wanted to do is, if I had the time, which unfortunately I do not. I do not have enough time to do this because I don't work on Odin as full time. And I don't know if I would want to work on Odin full time for numerous reasons actually, but that's a different thing. Is that I would probably have to write my own backend from custom to have another backend. And the Odin backend, this custom backend would be do minimal optimizations just because it would be aimed to be a fast compiler. It would not aim to be heavily optimized one. Someone's asking, it could be implemented with computed properties like Swift. So Odin does not have that because Odin has no concept of that. Data is plain old data. So theoretically you could do that, and theoretically you could, if you wanted that, to be honest with you, you could just have your own function. You could have a function that's called this, yeah? You could have a vector, and you could make it complete generic, by the way. You could just do this. Oh, it's going to be a for t where n is less than or equal to 4, and then you just do this. So you just go, okay, return return v.x, 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 v.x. And you could just do that in Odin. But this is all just about sugar. So that function would work like that, and you'd get the same thing. It just looks backwards to what you'd want, which is that. But yeah, so the thing is though, can you guess how many functions you'd have to implement to get that correctly? Yeah, it's a lot. So technically you've got 4 different combinations plus another set, but ignore the other set, but so 4 combinations, 4 positions, it's 4 to the power 4 4 to the power 4 is what, about, was that 256, I think? Yeah, so you'd have 256 different combinations, which is a lot if you were writing them manually. So, it won't be pretty, but it might be useful. But I don't think it would be actually, I don't think it would be more useful than just having this swizzle. I don't think it's actually as useful as you may think in practice. But yeah, so hopefully I've answered the question of the guy that wanted alternative backends to LLVM. Fortunately, there is no alternative other than like GCC for an optimizing backend. But if I wanted a fast backend, I could probably make my own quite not simply, but about a month's work, to be honest with you, to have a fast single backend thing. But I should state that if I'm aiming to get the Odin compiler to work in Odin, at least the front end, I will need to do a lot of this crap. Anyway, so that means, yeah. So I'm going to leave in literally 20 seconds now. So thank you all for watching, and thank you for tuning in for another day of Odin's Wednesday, and I'm giving you a high-level overview of the compiler's front end for Odin. If you would like to see this again, please just ask me, and that would be wonderful. I can do this again probably next Wednesday, of course. Or if you want to do that earlier, like you want to, hey, I want to work on the compiler, I want to help you out with the compiler. If you want to help out with the compiler, just go to the GitHub page for Odin. Just type in github.odin, like github.com/odin-lang/Odin, and you'll find it there, or you can get it on the Odin website, which is odinlang.org, and then click on GitHub and you'll get there straight away. If you want to help out, it's fine. If you want any more help if you want to learn how to use the compiler so you can actually make modifications, please do. The thing that needs work for the most is mainly the new LLVM API backend. We need to support, the two things we need to support is more platforms and debug information as well. The Windows backend, for the Windows platform for LLVM API, new one, is pretty good now. It's able to compile most things on Windows, same as the current one. It just does how to know debug information, and we do not support the other platforms yet, because I do want to replace the old LLVM backend, which I just outputted as text, with this. So thank you all for watching, and have good night and good evening and good morning and whatever time zones everyone in. So cheerio everybody, and praise the Lord that is Odin on his day, and now his son's day, which is Thor's day.